Hello, welcome to the second recording. We're talking about oxidation reduction reactions here. So an oxidation reduction reaction is a reaction in which electrons are transferred in the reaction from one atom to another. And so we've talked about ions in the past, and like how sodium forms 1+ ions or calcium forms 2+ ions. And so that means it loses electrons, or like the halogens gain an electron. And so if that happens in a chemical reaction, it's an oxidation reduction reaction. So any element in its elemental state is going to have the same number of electrons and protons, so it's going to be neutral. Like if we look at this reaction, okay, I have zinc. Okay, zinc is in its elemental state, so the charge is 0. It has the same number as protons as it has electrons. When it reacts with this copper 2 chloride, it becomes zinc chloride. So now since it's in a compound, it has a 2+ charge. So the zinc lost electrons. And the copper here was in a compound, so it had a 2+ charge. Here, it's now in its elemental state, just copper, so now it has 0 charge. So it went from 2+ to 0, so that means it gained electrons. So I had the zinc losing electrons and the copper gaining electrons. So electrons were transferred in this chemical reaction. So that's what an oxidation reduction reaction is, or known as a redox reaction. So the atom or ion that loses electrons, which in this case zinc is being oxidized, atom or ion that gains electrons is being reduced. So oxidation reduction always takes place together. We can split up the reactions into what's known as half reaction to show the oxidation and show the reduction. So if I look here, the loss of electrons, so my zinc's going from 0 to 2+, so I'm showing that in this half reaction. Okay, here is 0, here it becomes 2+, and I lose the 2 electrons. Copper is 2+, it gains the 2 electrons, so it becomes neutral. So loss of electrons, oxidation, gain of electrons, reduction. So you need to know that. You need to know, okay, it's loss of electrons, why is it? What's gain of electrons called? So there's a couple different ways to remember this. And so one is knowing what's an oil rig, with oxidation is loss, reduction is gain. The one I always remember is Leo with the line goes GER. So Leo, loss electrons, oxidation. GER, gain electrons, reduction. Now, the reducing agent, we can also have, okay, what's oxidized and what's reduced. The other two terms are reducing agent and oxidizing agent. So a reducing agent causes reduction by losing one or more electrons and undergoes oxidation. So a substance that undergoes oxidation is causing the other one to be reduced. So that substance that undergoes oxidation is your reducing agent. Likewise, the one that causes oxidation in itself is being reduced is your oxidizing agent. So let's look at this reaction. So consider the following reaction. Zinc plus copper sulfate yields zinc sulfate plus copper. So zinc oxidized or reduced. So I'll look at zinc, elemental state, oxidation number 0, charge 0. Here, sulfate's a 2-, zinc must be a 2+. So zinc went from 0 to 2+. So if it went from 0 to 2+, okay, that means it lost electrons. Loss of electrons is oxidation, so zinc is oxidized. Copper, here it's 2+, here it's 0. So it went from 2+ to 0, must have gained those electrons. So gain electrons, GER, gain electrons, reduction. So copper is reduced. Whether an atom or ion is a molecule, compound, or an elemental form, it can be assigned an oxidation number. And that's what we've been doing this whole time when we was naming compounds, saying if it, is in group 1, it has a +1 charge. That's its oxidation number, or also known as oxidation state. So here are the basic rules for assigning the oxidation numbers. So some of them can be different. So we'll see some elements in the periodic table can have more than one oxidation state. And we've seen this before with some of the transition metals, you know, how iron can be a 2+ or a 3+. So we've seen this before, but we'll also look at some of the non-metals now. So here are some of the basic rules for assigning the oxidation state, the oxidation number. Any atom in its elemental state has an oxidation number of 0. So if it's an element, oxidation number 0. An atom in a monoatomic ion has an oxidation number identical to its charge. So wherever the charge is, oxidation number. Now here, if it gets into a polyatomic, usually it has the same oxidation number as if it was a monatomic ion. Okay, but what you look at, hydrogen can be either +1 or -1. Oxygen's usually -2. Halogens usually have -1. And from there, you can figure out your others. The sum of the oxidation numbers is 0 for a neutral compound and is equal to the net charge for a polyatomic ion. So if you're figuring out the charge on a polyatomic ion, or the oxidation numbers for the atoms involved in a polyatomic ion, the total will equal the charge on that polyatomic ion. So we'll look at some examples of that later on. Let's go ahead and look at this one right now. So determine the oxidation number of phosphorus in Na3PO4. So sodium phosphate. Well, I know sodium is a plus charge, and I have 3 of them. Okay. I know oxygen is a 2-. Okay. And I have 4 of them. So 4 times my 2-, that's going to give me 8- total. So what must, I know all of them added together is going to be 0. So what fits in here that makes this equal to 0? Okay, so that'd be +5. So I know my oxidation number for phosphorus then is +5. Okay. So another way you could have worked this, or seen this, is determine the oxidation state of phosphorus in the phosphate ion. Okay, you're going to get the same answer, but this time I do it the same way. With phosphorus, oxygen, I have 4 of them. It's a 2- charge, so it's 8-. Okay. Well, here though, my charge is a 3-, and so what plus 3, 8- would give me 3-. So +5. Okay, so get the same answer because the oxidation stays the same, but this is what it means by if you have just a charge there, you say equal to that charge. If it's neutral, no charge, you say equal to 0. Look at the activity series. And this goes back to where we talk about the active metals, the ones that react with hydrogen or react with acids, the metals that react with acids to give hydrogen. So the activity series of metals ranks the elements in order of their reducing ability in aqueous solution. Any element high in the activity series reacts with the ion of an element lower in the activity series. So this is really talking about single replacement reaction. Will this reaction happen or not? And you can use this table here. And so you do not have to memorize this table, so I'm not going to give you any problems on the exam that where you have to use this table. But you may see this problem on like your homework or something. So if I look at this, it says using the activity series, which of the following reactions will not take place? So I'll look at this first one, aluminum zinc. So if I did a single displacement reaction, aluminum replaces zinc. So anything high in the activity series will replace something lower in the activity series. So I locate aluminum and zinc. So here's aluminum, here's aluminum, here's zinc. So aluminum's above it, and so aluminum will replace zinc. So that one will react. Now the next one's nickel and iron. So nickel plus iron 2 nitrate. So I'll look up iron. I'll look up nickel. Iron is nickel. Nickel's the one that would be doing the displacement. That's the one I have the element of. So nickel is not above iron, and so that reaction will not work. Okay, so the one that's doing the displacement has to be higher than the other one. There's nickel and hydrogen. So if I look at nickel, here's hydrogen, so nickel is above it. That one would work. Okay, so nickel's one of the reactive metals. Here are some common examples of redox reaction. Combustion is a common example of redox reaction. You have a transfer of electrons. Corrosion, iron becoming iron oxide, so iron's going from a 0 charge to a 2+ or a 3+ charge. Leaching is an example of a redox. Batteries, how batteries work, that's a redox reaction. Breathing and many biological processes are examples of redox reactions. Photography is another example. And so I'm going to finish up this little tidbit of the lecture with assigning oxidation numbers, just some more practice here. So assign oxidation numbers to all elements of following compounds. And ion, just have one ion there. So this one's fairly easy. Lithium oxide. So oxygen's a 2-, lithium's in group 1, it's the same as the charge, so lithium, or just have the plus. Okay. HNO3. Now this one's where I actually have to calculate that. Okay. So hydrogen I know is a plus. Oxygen I know is a 2-. So if this was a plus, this was a 2-, and 3 of them, that would be a 6-. So what would fit in there? Okay, so I have 1+ and a -6. What would make that equal to 0? A 5+. So in this case, nitrogen is a 5+. Cr2O7, same thing. I know oxygen's a 2-. They have 7 of them. So that's a 14-, or you can say -14. Chromium, okay, I have 2 of them, okay, so 2 times what -14 will give me the charge of this. So the charge, well, not here, it's oxygen, here is 2-. Okay. So if this is -14, and I want a charge of -2, then I need a +12 here, so I need a +12 here, but I have 2, so 2 times what would give me +12? So 2 times 6. So 2 times 6 would be +12 -14 would be the -2. So that means chromium has to have a 6+ charge in that molecule. Another type of questions you'll see on the exam is I'll give you some different reactions. I say which ones are redox reactions or which are not redox reactions. So you have to look and see, okay, does the charge change on any of them? And a lot of them is fairly easy to know, because if you ever see something that has a elemental state, plus then it shows that same element in a compound, then you know the oxidation state's changed since a redox reaction. So here, element, compound, element, compound, element, compound, element, compound. I know all those are redox reactions because they have element on one side, compound on the other. It says here, classify the following redox reactions, indicate changes in the oxidation numbers of the elements. So let's do that. So here I have N2O. So here I have N2O. So I know oxygen's a 2 minus. And so the charge is just 0. So it balances out. So 2 times 1 would give me 0 plus 1. And so nitrogen goes from plus 1 to 0. Okay. Oxygen goes from 2 minus to 0 because it goes to an element as well. Okay. So plus 1 to 0 is a gain of electrons. Minus 2 to 0, that means they had 2 extra, now it lost those. That's a loss of electrons. So Leo the lines, oxygen's oxidized, and nitrogen in this case gained electrons, so it's reduced. Okay, how about this one? So here, lithium, I know it's in group 1, so I know it's plus 1. Nitrogen, okay, if this is plus, nitrogen must be a 3 minus. So here they're in the elements, so they're 0, so lithium goes from 0 to plus 1. Nitrogen goes from 0 to 3 minus. Okay, so in this case, lithium 0 to plus 1, that is a loss of electrons. 0 to minus 3, that's a gain of electrons. So lost electrons, oxidation, so lithium is oxidized, nitrogen is reduced. Last one here. So nickel, 0, lead, 0. If nitrate's minus altogether, okay, I know lead's a 2 plus, in this case nickel would be a 2 plus. In this case nitrogen has I know the nitrate has a minus charge. I know oxygen's a 2 minus, so 3 times a 2 minus would give me 6 minus. So if it equals minus 1, nitrogen must be a plus 5. Oxygen's your 2 minus. So it's going to stay the same over there. So the ones that are changing are the nickel and lead. So nickel goes from 0 to 2 plus. Lead 2 plus to 0. So nickel 0 to 2 plus, that's a loss of electrons. So loss, oxidation. Here 2 plus to 0 is a gain of electrons. So lead is reduced. So that's it for this video. And we'll look at concentrations and start looking at some calculations involving concentrations on the next videos. Bye.